Thank you. I'm delighted to be here and open this fantastic lift and escalator symposium. I come from Kone Corporation, and I'm going to share with you some results of an extended research project about a fascinating subject, high-rise lifts, which implies high-rise building, which mean to me beautiful architecture, innovative solutions, and amazing travel destinations where I hope that I will go during my lifetime. This paper has been written together with several departments. I'm from Right Comfort department in Kone. My colleague Jaakko Kalliomäki, platform manager. Mirko Ruokokoski is working for traffic and people flow. Jarkko Saloranta is our technical support. And Vishnu Srinach was my master student during the last year. The outline of this presentation, it's a little, looking, as you can see, starting with the introduction, why we did this research, continuing with the computational strategy, how did we choose the computational strategy, and then focusing on three aspects of the results: impact of velocity profile on in-car vibrations, impact of building sway on in-car vibration, and impact of velocity profile on lift performance. In the end, we will finalize with conclusions and discussions. So why did we start this research? The reason is that because of mega trend of urbanization, the lift industry is facing two different demanding requirements. One is to have very short travel, and the second is to have high safety and comfort. And the solutions to achieve these demands are not all the time aligned. On top of this, the very tall and thin buildings give us more challenges because the building response to strong wind condition or other excitations have an impact on the lift performance. Therefore, our challenge was to find a solution to improve our customers' comfort during building sway conditions. And our solution was to develop the methodology to compute in-car vibrations, and after this to analyze the impact of our solution on building, on lift capacity, on lift handling capacity. So this is the presentation for today. The first challenge was how to choose the computational strategy, because we are analyzing a 500-meter tall building, which means very long guide rails and also very detailed components and very small in-car vibrations. And in the beginning, we are considering multi-body simulation. However, because we have a lot of flexibility in the components, we decided to go with finite element, and we choose the transient dynamic analysis for this case, where the car is moving with a variable speed and covers all the travel. We still had a very big model, and because we are working for a company and everyone needs the results very fast, eventually yesterday, we had to decrease the computational time. And for this reason, we choose dynamic substructuring, which means that any component that could display a linear behavior could be computed beforehand and reduced to a very small matrix of mass, stiffness, and damping, which is then involved or included in a system-level simulation. So structuring is not a new feature in finite element, but it's a very powerful one, and we decided to use it. So one very good candidate was the guide shoes. We have 4 guide shoes in a lift around the sling, and these guide shoes could be computed beforehand. The only component in the guide shoes which is not linear are the levers, because they are hitting the stoppers and they are displaying an angular movement. Therefore, the decision was that the body of the guide shoes were creating a substructure, and the levers were creating a different substructure. In the substructure, we could have several loading cases. And for the guide shoes, we had contact with the guide line. And also we had a frequency extraction to understand what's happening inside the structure. The second substructure that we could consider was the sling and car component. This also behaves linearly. We can assume that it has a linear behavior. And the loads that we could apply for this substructure were gravitational load, frequency extraction, and then a pressure load due to the counterweight passing by. And this counterweight passing by was computed also beforehand using a transient fluid dynamic computation. And this was also reduced to a small matrix of nodes. The next challenge was the guide rail. And you can see that the sling and car are very small for 500-meter tall guide rails. So this was an additional challenge. And we decided to use for these guide rails, we decided to use beam elements with variable profile to take into account the fish plates. And then for brackets, for connecting the guide rails to the walls, we choose springs that we calculated the stiffness of the brackets beforehand and added in the model. The guide rail misalignments, which are of decimals of millimeters, so very, very small, they were induced in the model by using an user-defined subroutine, which is explained in detail in another paper. These misalignments were measured on the sides, on various sides. And in addition to the misalignments, we need to add the displacement of the building due to the sway. And all of this data we collected from architectures and architects and also different kind of buildings that we analyzed. Next challenge were the ropes. We have a lot of ropes and traveling cables in our system. The ropes were modeled as user elements with variable mass, and the loads due to the rope sway were calculated beforehand using finite difference method and were added in the model. And finally, we had the variable speed profile for the car running up and down. So big model, and we had a lot of challenges and a lot of trials to find solution to compute it very fast. Therefore, this is how the model is looking like. We have 1,000 scale in the first picture, and we have the building swaying and the car moving inside the building. This is how the model looks like with all the substructuring. So very, very concentrated and simple model, so we can run it fast in about 5 hours. This is how the substructure looks like. So even if we have this system analysis, we can go inside the substructure and see what's happening during the entire run. And this is the other substructure the guide shows. So we found a solution that was fast and also give us details of what's happening during 10 meter per second travel, 500 meter distance. After this, when we had the results ready and they were in correlation with the test, we tried to analyze what can we do with these results. And we started with 10 meter per second speed, and we analyzed what is in-car vibration. And as a criteria, we choose 10 GARs or 10 milli-Gs, distance between adjacent vibrations in car. And we find out that if we choose 10 meters per second during the sway of the building, during strong winds, we cannot reach this right comfort criteria of 10 GARs. The traditional way to do it is to decrease the speed from 10 meters per second to half, to 5 meters per second. And we analyze this case, and we find out that we fulfill the right comfort criteria. However, the time increased from 70 to 120 seconds, and this was a little bit too much. Then we started to play with the speed and see what's happening if we have different profiles. If we don't have 10 meter all the ride, but we can choose to decrease the speed in the middle of the run. And we had several options, and our master student analyzed in the end 19 cases. He analyzed many more, but 19 cases were taken into consideration in this paper. And out of these cases, one of the solutions was choosing as the best, fulfilling both of criteria: good ride comfort and acceptable flying time. In addition to this, the second analysis was how the building sway affects in-car vibrations. And we find out that if there is no vibrations inside, if there is no sway, the vibration inside the car are how we are expecting and how we measured. However, if we add the sway, even in the beginning we have 44 millimeter amplitude at the top of the building sway, we could see that even when the car stops, the building is still moving and we can measure vibration inside the car. However, in the beginning of the run, there is no difference because at the foundation of the building, there is not so much impact of the sway. In the end, we tried to find different amplitudes and analyze what's happening, and we ended up with 88 millimeters, 66, 53, and 44. And we find out that if the sway is under 53 millimeters, the impact on in-car vibration is quite small. However, if it's higher, then we need to change the speed and do something to fulfill the right comfort criteria. So only at the top of the building, where the building is flexible, we need to do something. Then we analyzed what is the impact of this proposed velocity profile on handling capacity. And with the help of Mirko, we analyzed two groups, theoretical groups of elevator, of lifts. First, it's a shuttle, and it has 4 lifts. And second, it's a group of lifts that serve the top 20th floors of the building. We had 3 speeds that we analyzed. And now at the bottom is not time, it's the height of the building. And the first speed is 10 meters per second, which was the traditional, the normal speed of the lift. The second is 5 meters per second. And in the middle is the proposed optimized speed profile, where only at the top of the building we decrease the speed from 10 to 4 meters per second. Then we analyze several traffic patterns, and the results are displayed below. It is obvious that if we use this variable velocity profile, we can increase the handling capacity, and also we can decrease the waiting time of the lift. And the results are more important for shuttle group of lifts. However, this was not enough, and our platform manager wanted to know what is the impact during the entire year of this velocity profile on handling capacity. And analyzing weather conditions, we find out that there are 4 distinct modes that could be used during the entire year. First is when we have normal weather, and we can use clearly 10 meters per second with no challenge. Then when the weather is not so good, so we have stormy weather, and the sway of the building it's up to 88 millimeters, then we can use this variable velocity profile that we called enhanced sway mode. For high wind, and also the traditional way of decreasing the speed to half, this is called high wind mode. We can use the 5 meters per second speed profile. And then the storm mode, where we don't use the lifts whatsoever. We park them in a safe floor where no resonance is probable. We analyzed the meteorological data during 1 year, and we find out that the number of hours for which these weather conditions are important are, for normal weather, 8,729 hours per year, for high winds, 30 hours, and for storm, less than 1 day, so several hours. For this specific building in this specific position of the Earth. Then we calculated the yearly handling capacity by taking into account the possibility to have all these weather conditions. And we compare between the group A of shuttle lifts and group B of lifts serving the top 20 floor of the building. And we find out that the impact during the year is not so high, which means that we don't have enough stormy weather during 1 year to have a significant impact. However, the handling capacity is more significant for the group of shuttle elevators. Conclusions. This transient dynamic computation enables us to analyze in-car vibrations for a much wider perspective, because we can take into account ride comfort criteria, we can take into account traffic calculation, we can take into account weather, and also building characteristics. The results show that for 10 meters per second during strong winds, we have unacceptable in-car vibrations. If we decrease the speed to 5 meters per second, we have acceptable vibrations, but then we don't have short enough travel time. And only the top of the building, it's important to have the speed reduced, and also only for a certain amplitude of the sway, it's important to reduce the speed. In the end, we had this optimized speed profile, and we could see that studying using building traffic simulation, by using this velocity profile, variable velocity profile, we can increase by 30% the traffic handling capacity during the strong winds. However, since the winds, the bad weather is not all over the year for this specific building, the increased capacity is very small for the entire year. And besides this building sway analysis, the model that we have built can be used for product development, for predicting in-car vibration, for changing the components and seeing what is the impact on the car, and so on. Thank you.